So yeah, we are getting 0.25%, and then we can calculate. We can use our Hooke's law, and we can get the yeah, we can calculate the we can use the Hooke's law, and then we can get the sigma allowable. So sigma allowable will be E times epsilon allowable, which is 16,000 psi, and from that we can get the P allowable. So P allowable 2, which is sigma allowable times area, which is 16 into that area, which is 3136. So the allowable stress is chosen such that it will be smaller of these two values. So 3337 and 3136, the smaller one is this value. So as long as P value doesn't exceed this value, both these conditions will be satisfied. That is, the allowable stress will be less than 17,000 and the allowable elongation will be less than 0.04 inch. Okay. So this concludes one part of the part of the class. Now we'll go to the next part where we will discuss axially loaded members. That is, members which are subjected to tension or compression, like a pure tension and pure compression, and we are going to find the changes in length which can take place. So this part is basically we are moving to the chapter 2 of the textbook by James Gare. So you can refer to that also. So let's start with the learning objectives for this part. So basically we're measuring the changes in length, and we will be studying prismatic. Prismatic bars. So for prismatic bars, there is uniform stress and uniform strain throughout the bar. So that is a uniform strain problem. And then we will study non-uniform conditions. So when you say non-uniform conditions, there can be divided into three categories here. So one is bars with intermediate axial loads. So the bar is prismatic and axial loads are acting in between the bars. And the second case will be bars with bars made up of segments, multiple prismatic segments. So certain part of the bar has one cross section area, another part of the bar has another constant cross section area. So when you are assembling those kind of bars and subjecting them to loads, so what will happen? So again, there will be some non-uniformity coming there because the areas are changing, and probably if Young's modulus are changing, that also will cause some changes in the axial strain. So the third case is the bar is varying continuously. So you can think of like a cone shape, or that is bars with continuously varying dimensions. So the cone is a continuously varying dimension, or you can have continuously varying loads. So suppose there is self weight acting on the bar. So the axial force within the bar will keep changing at every cross section. So for these kinds of bars, then there will be non-uniform strain. So we'll be looking at all these problems in this class. So let's begin with the first case, which is the prismatic bar. So in the prismatic bar, we have a bar of length L, and it has Young's modulus C, area of cross section A, and yeah. So we apply a load P on the bar. Because of this applied load, the bar will elongate by small amount delta. So we can calculate the stress in the bar, which is sigma is P by A, and this stress is uniform throughout the length of the bar, and we can calculate the strain. Strain is total elongation by initial length, so delta by L. Again, this strain is uniform throughout the bar. That means strain here, strain here, strain here, anywhere is delta by L. So this is a problem of uniform stress and uniform strain. So we can use our Hooke's law, sigma is E epsilon, and then we can substitute the values, and we can get delta elongation in terms of P and E and A. So it is delta is PL by EA. So we see that elongation is proportional to the applied load, and also elongation is proportional to the length of the bar, and elongation is inversely proportional to the value of EA. So EA is also termed as the axial rigidity of the bar. So the elongation, so higher is the axial rigidity, lower is the elongation. So we'll now define two terms called stiffness and flexibility. So what is stiffness? Stiffness is the force required per unit elongation. So here force is P and elongation is delta. So P by delta is the stiffness. So stiffness is denoted by the letter K. So P by delta will be EA by L. And also we can look at the term called flexibility. So flexibility is the elongation per unit load. So elongation is delta and unit load is P. So delta by P is the flexibility. It is denoted by the letter F, and we have flexibility as L by EA. So stiffness is actually directly proportional to the axial rigidity. Flexibility is inversely proportional to the axial rigidity. These two, stiffness and flexibility, are used later in advanced structure analysis, where you will learn about matrix methods and you'll assemble stiffness matrix or flexibility matrix for large scale structures. So this is usually done. This course is offered to the civil engineering students in I think seventh semester, I think. So yeah, this is regarding the prismatic bars. So this is a very simple calculation. Now we'll look at little complicated one where we have bars with intermediate axial loads. Okay, so just 1 minute. Okay, so bars with intermediate axial loads. So here we have a bar A. Here we have a fixed bar, prismatic bar. Okay, and what is happening is this bar is subjected to loads not only at the end but also at some intermediate points. So here we have a load at the end PD, and intermediate points C and B. We have two loads. One load acting PC like this, another load acting PB upward. So how to analyze these kind of problems? So first thing we'll do is we have to divide this bar into segments. Okay. So how will you divide the segments? The first thing we'll look into is the axial force, n value. The n value will be such that it is usually constant in that segment. So for this case, we will divide the bar into three segments. Okay, segment AB, segment BC, and segment CD. Okay, so the lengths are L1, L2, and L3. So once we divide this bars into these three segments, then we will look into the axial force. Okay, we'll calculate the axial force along this segment. Okay, segment 1 along segment BC and segment CD. So how do you calculate the axial force? So the simplest way is to cut the segment A. So we will cut the segment A, and then we will look into the free body diagram for the bottom portion. So we have this bottom portion, and here the forces are PD, PC, and PB. Okay, so to balance these forces at the top cross section, at this cross section, there is a tensile force. You can assume that there is a tensile force acting in the upward direction. So let's call the tensile force N1 because we are referring to segment 1. We will denote it as N subscript 1. So using force balance, so N1 will be equal to PC plus PD minus PB. Okay, so if you do the force balance in the y direction, we'll get this relation. So if you look carefully here, as long as PC plus PD is greater than PB value, we will have that PC plus PD is greater than PB, then N1 will be positive. That means N1 is a tensile force. If suppose PC plus PD is less than PB, then N1 will be negative. So we have to reverse the arrow and it will act in the downward direction. Okay, so then it will be a compressive force. So for now, we will assume N1 is positive and the direction to be like this, and PC plus PD minus PB is the tensile force here. So if you cut the cross section anywhere in segment AB, if you cut it here, you cut it here, and cut it there, and do the analysis, you will get the same value for N1. It will be PC plus PD minus PB. So along in the segment AB, the tensile force, that is axial force, is constant, and it is equal to this value. Now we can cut the segment BC and see what happens here. So we are cutting the segment BC. Now we will analyze the lower portion of the bar. So in the lower portion, again, we have the two downward force, PC and PD. Now PB will not be part of this problem. Okay, so only there are two forces, PC, PD. And at the top circular area, we will have the normal force N2. So this N2 value will be balancing this PC and PD. So N2 will be PC plus PD. Again, this N2 value will be uniform throughout this segment BC. Okay, so if you cut the cross section here, or if you cut the cross section there, you will have same value for N2. So here N2 will be a pure tensile force. There is no possibility for it to be compressive because PC and PD are always downward, so it has to be always tensile force. Now we'll look into the third segment, and we cut a cross section there, and now this is the free body diagram for the bottom portion. We'll have this PD value, and at the top cross section there will be a axial force N3, and again if you want to do a force balance, you will get N3 is equal to PD. Okay, so this is the tensile force in the bar. Now what we'll do is, once you have found the axial force, then we can find the elongation in each bar separately. So to find the elongation in bar in AB, so this is a prismatic bar with a tensile force N1. So length is L1. So we can apply our formula delta 1 is equal to N1 L1 by EA. EA is the Young's modulus and the axial area of cross section for segment AB. So again, we can do a similar analysis and get the elongation for bar BC. So how to do that? We'll simply take delta 2, that is elongation of BC, as N2. N2 is constant throughout this segment. So N2 L2 by EA. So this is a formula for the prismatic bar. And again, if you want to find delta elongation of segment CD, we apply delta 3 is equal to N3 L3 by EA. So the total, we have found the elongations of the individual segments AB, BC, and segment CD. So these are delta 1, delta 2, delta 3. Now we can sum up all those 3 elongations and get the final elongation delta. So delta will be sum of these 3 values. So this is the case where we have a prismatic bar, but it is loaded intermediately with different axial loads. So now we will look at the another case. So here we have a bar which is assembled by assembled with 2 prismatic segments. So here AB segment is has different cross section area, and probably it can have a different Young's modulus, and BC has different cross section area and it can have a different Young's modulus. So again, here now force is applied only at the end. So if you cut a cross section, so how many segments we need to do for this problem? So how many segments is because axial force is same here and here, but the thing is that area of cross section is varying from A to B and B to C. So we have to cut into 2 segments, segment 1 and segment 2. So we have to make sure that strain or N by EA is constant in that segment. So again, once we divide the bar into segments AB and BC, we'll again we'll analyze the axial force coming in segment AB. So how to do that? We cut the cross section in segment AB and then draw the free body diagram for this portion. So here we have this force PC downward, and to balance it, there is a tensile force N1 acting there, and that value is PC. And again, we want to find this tensile force in we want to find the axial force in BC. So again, we cut a cross section there and find the N2 value, which is also again PC. So we have found this tensile forces. Now we'll calculate the deflections of this prismatic bar AB. So how do you do that? You just apply that formula. Delta 1 is N1 L1 by E1 A1. So here we have to be careful because Young's modulus E1 will be different for AB, and A1 is the area cross section for segment AB. Again, we can calculate the deflection for this segment BC, which has this constant N2 acting throughout the segment BC. So we'll get delta 2 as N2 L2 by E2 A2. So the total change in length will be sum of this delta 1 plus delta 2. Okay, so that is the elongation for this prismatic bar. Now we will look into another part of the problem. So here what we have is 2 prismatic bars which are assembled, and they are of different material, and we have intermediate axial load on the first member acting in the upward direction. Okay, so how many segments we need to divide this problem into? So anyone can answer this?
Three, sir.
Why you need to divide into 3? Okay, I have given the
different materials and 2.
Huh? Yeah, why we need to divide into 3 is because we need to look for this problem of N by EA should be constant. Okay, so first thing is we need to divide into 2 elements. Minimum segments required is 2, AB and BC. But if you look carefully at AB, there is this point load acting upward. So the tensile force in this part will be different from tensile force in BD. Okay, so there will be different tensile forces here. So we have to divide this bar into 3 segments. Okay, segment AD, BD, and PC. Now, if we divide this bar into 3 segments, and we'll do the analysis. So we'll solve it as a numerical problem. So we are given the AD and BD values as 1000 millimeters, and Young's modulus as 1000, area as 100. And for portion BC, length is given, L3 is given as 2000, E is 2000 Newton per millimeter square, area of cross section is 200 millimeter square. And what else is given? We are given the value for PD, that is applied load, which is 400 Newton, and hopefully it is okay, PD or PC. And PC is 200 Newton. I think the small error here. I think this is 200, I think. It should be 200 and 400. It's okay. Let's say it's 400 and 200. Okay. So PC is 200. No, sorry. PC is 400. I'm sorry. Previous slide it was wrong. So PC is 400 and PD is 200. Now what we'll do is we will calculate the axial forces in the bar. Axial forces in each segment. Okay. So let's look at segment AD. So what we do, we cut a cross section in segment AD here, and then we look at the free body diagram. So we have PC down and PD acting upward, and here we'll apply some force N1. Okay, that is the axial tensile axial force acting on that cross section. So if you do the force balance, N1 will be PC minus PD. So PC minus PD means 200 minus 400, which will be a value of minus 200. So what does this show? That what does it mean? Minus 200. It means that it is actually a compressive force. So this member AD will be subjected to compression throughout the
200.
throughout the length of the bar. Okay. So that is the N1.
PC is 400.
I'm sorry, that one was. Yeah, I think I confused them. 400, I think. I'm sorry. I think this PC should be 200. I think for this problem.
Actually, we have to do
Is correct.
PD minus
I think PC is. PC is
here PD minus PC.
already error here.
So you are muted, sir.
So yeah, N2 value is 200 here, and we'll cut the segment BC, and here N3 value will be 200. Okay. So with this information, we will look into the we'll draw the axial force diagram here. Okay. So yeah. So PC was actually what? PC was 200 and PD is 400. Okay. So we'll draw the axial force diagram. So axial force diagram will have N1 is minus 200, and between BD the segment it will be 400. Oh, sorry, it is 200 or 400. So let's change it and make it 200. So I hope I can rectify those. I have rectified those errors here. So yeah, N1 value here was minus 200, N2 value is 200, and N3 value is also 200. So this part is shown in the black color, and it is a negative value. So it is minus 200, which is a compressive force. And here in segment BD, we have a tensile force. So it is shown in the positive. It is shown with a red color, and it is on the other side of this line. And N3 value is also constant 200. It's acting on the other side of the line. Okay, so yeah, that's what we have. Now we can draw the axial stress diagram. So stress value will be sigma in this segment. So it will be N1 by A1. So A1 value is 100. So stress in this portion will be minus 2. Okay, and stress in this portion segment BD will be it will be plus 2. Okay, and here the area of cross section is 200. So 200 by 200 it will be 1. So the stress in this portion will be segment will be 1. So this is the axial stress diagram in the bar A in this bar. Now we can apply our Hooke's law and get the strain in this bar. So how do you apply the Hooke's law? We will calculate the strain axial strain diagram, and we take sigma 1 by E1. Okay, here E1 is 1000, so it will be minus 0.002, and here stress is 2 and E1 is again 1000, so we'll get a positive strain of 0.002, and here sigma 3 is 1, but the E value is 2000. Okay, so we have to divide 1 by 2000 and we will get a 0.35 by 10 power 4. Okay, so this is the axial strain. I think 5 is missing here, but this is the axial strain in this bar. So you see that there is a non-uniform strain distribution along the bar. So we have a compressive strain in this portion, then we have tensile strain in this part of the bar, and then another tensile strain. And there is a jump in the tensile strain here, and there is a jump from tension to compression at this point. Okay, at point D. So with this strain diagram, we can calculate the change in lengths. So change in length will be delta 1, which is for the segment 1, change in length will be delta 1, which is equal to E1 L1. Okay, so what is the change in length here? So length is 1000 millimeters, so change in length is 2 millimeters, so it's minus 2 millimeters, and here it is 1000, so it will be plus 2 millimeters, so minus 2 plus 2, and this one is 0.005 into 2000, so it will come around 0.5 into 2, it will be 1 millimeter. So the net elongation will be minus 2 plus 1, so it will be around 1 millimeter. Okay, so this is regarding the use of axial force diagram and how to use an axial stress diagram and axial strain diagram to calculate the elongations in the bar. So in all these problems, we have either prismatic cross sections or assembled prismatic cross sections. Okay, so we'll be going to the next part of the class. So in this, so just let me take a break for 30 seconds. I'll come back. So yeah, so we'll go through this very quickly. So we are dealing with bars with continuously varying loads or dimensions. So in this problem, we have a bar, prismatic bar. It is subjected to external load P, and we are considering its self weight. So self weight is the is due to gravity. Okay, so we have to consider for this self weight. So we have a axial force distribution throughout the length of the bar, and this will produce a non-uniform axial stress distribution and therefore a non-uniform strain distribution. So this is one case we'll study. Another case we'll study is of a conical bar which is fixed at one end and it is hanging freely. So we are looking at what will happen, what will be the deflections and all, and what is the axial stress distribution and strain distribution here due to its self weight. Okay, so these two problems we'll study in today's class. So let's begin with the first problem. So here we have this bar which is subjected to this self weight and also the external load. So under the action of the self weight and external load, this is the undeformed shape of the bar. The properties of the bar are given as EA, rho, GL. E is the modulus of velocity, A is the area, rho is the density, G acceleration due to gravity. And this is the undeformed shape. And under the action of the load, the bar will deform. So here the deformation, total deformation is given as delta of L. Okay. So we are interested in delta of X. So what is the deformation at each point? Okay. So the elongation at each point. So this elongation is not constant throughout the bar. It will keep varying because both the axial load is axial stress is varying throughout the bar. So how to find this delta of X? So what we do is, since all the stresses are varying throughout the length of the bar, we have to divide this bar into infinitesimally many segments. Okay, we have to divide into many segments. We can't do that, so we have to use a calculus-based approach. So in calculus-based approach, what we will do is, we will take a small segment of length dx at a distance x. Okay. And then we will see what will happen to this dx element under the application of load. And so what will happen is, under the application of this load and all, this this part of the bar which has initial length x has deformed to x plus delta. Okay. And this part, the small infinitesimal segment dx, has deformed to dx plus d delta x. Okay. So this is the elongation in this infinitesimally small element. Now, what is the strain in this infinitesimally small element? Can anyone tell? What is the initial length of this? Yeah. What is the initial length of this segment? Yeah,
Sir,
yeah.
someone is removing me from the group. That meeting, someone is removing me.
So we'll discuss that your problem later in the class after the, because you will anyway will get attendance. So I will record the class and you can listen to it. So yeah, so I asked you a question. What is the strain? What is the strain in this element? So we have the initial length dx, and it is extending to dx plus d delta x. So what is the elongation of this element? Hello.
D delta
X.
Yeah, elongation is d delta x.
D delta
What
X.
is the initial length?
Dx.
Delta x. So what will be the strain? D delta x by dx. Okay. Yeah. So this is the strain in this a small element. Okay. We have found the strain expression for strain here. Now what we'll do is, we'll calculate the axial force coming at this portion. Okay. For this x at location x. What is the axial force at location x? So what we do, we cut a cross section, and then we will look into the free body diagram. So free body diagram, we have our load P acting downward, and what is the another force acting here? I not shown this force. What is the force here, which is not shown? It is also acting downward. Weight. Yeah, it is the weight of the weight of this bar. Okay. So weight of this bar is taken as volume of this bar times rho times g. Okay. Rho times volume will give mass, and g mass times g is the weight. Okay. So the weight of the bar is acting down. Then at this cross section, we have our axial force n of x. Okay. It is acting in the upward direction. So we can use the force. We can do the force balance. So volume of the bar will be area of cross section times length L minus x. Okay. So that is the volume of the bar. So n of x value will be P plus rho g L minus x times A. Okay. So this is the axial force acting at that cross section x. Now we will look into the element and see what is happening there. So on that element, infinitesimal small element, we have this nx and nx acting, and this axial force is producing this stretch in the bar. So this axial force, yeah. So we can calculate the corresponding stress acting in the bar. So we know the area of cross section as A. So sigma will be n of x by A of x. So with this information, we will do our analysis. So n of x is written in terms of this quantity. So we can. So we have two relations first. First one is the strain expression for strain, which is d delta of x by dx, and second one is sigma of x is n of x by a of x. So we can we can calculate d delta in terms of strain value as like this: d delta is epsilon of x times dx. Okay. So using a Hooke's law, we can rewrite epsilon of x as sigma of x by e. Okay, and sigma of x is actually n of x by a of x, and so we'll get d delta as n of x dx by e ax. Okay, now we can do our we can substitute the expression for n of x here, and we get this expression p plus rho g l minus x a times dx by e a. We can do our now we do summation over and we do the integration from x is equal to 0 to x is equal to L. So what will happen is we will get delta of L minus delta of 0 on the left hand side, and the right hand side we are doing the integration from x is 0 to x is equal to L. So the first term will be p dx, so it will be pl by ea. Second term will be rho g l minus x a by e, so lx will become L square, and minus x will become s square by 2, which is L square by 2. So L square minus L square by 2, you will get L square by 2e. Okay, so this is the deflection PL by EA plus rho G L square by 2e. If you look at the dimensions, you can work out and you will get the same value. You will get a dimension for length. So here what happens, what is delta of 0? What is the deflection at x is equal to 0? So this point is connected to the fixed support. Okay, so this point will not move. And so the elongation at this point x is equal to 0 will be 0. Okay, and then we can get the delta of L as this value PL by A plus rho G L square by 2e. And if you want to find deflection at any intermediate point, we just replace L with x, and we have this expression Px by A plus rho G x square by 2e. So this is for analysis for a prismatic bar, which is subjected to self weight and axial load. Now we look at the problem of cone. Okay, so inverted cone, and we'll have again this cone, but there is no external load acting here. So there is only self weight of the cone acting here. So this is the undeformed shape, and we'll get the deformed shape. So in the deformed shape, again, this point has extended to delta of L. So the total length will be L plus delta of L. And we are interested in finding what is the elongation as a function of x. So what we do, again, we'll cut a cross section at x. I will take a small element at the x, and the length of the element is dx, and we'll see how that element will elongate under loading. So this part of the segment will extend by x plus delta x, and this part infinitesimally small element will extend by dx plus d delta x, and we have our strain values, change in length, which is d delta x, by initial length, which is dx. So this is the strain epsilon of x is d delta x by dx. Now we want to find the axial force acting at x. So we cut a cross section at x and draw the free body diagram. So this is the cone. This volume of cone is there, and the weight of this cone is acting downward. This portion of the cone is acting downward. So what is the volume of the cone? It is 1 by 3 pi r square h. Okay, so pi r square is r will refer to this radius, pi r square h, and we are having a axial force n of x acting, which will balance the weight of the cone. So n of x will be rho g volume. Volume of cone is pi r square, 1 by 3 pi r square h. H value is L minus x. So we can get the stress value for this infinitesimally small element. So this is the axial force n of x, and stress value will be sigma of x by a, n of x by a. So if you look carefully here in this expression, pi of r of x square actually refers to area of this cross section. Okay, so we can replace pi of rx square with a of x for this specific problem, not for every case. Only for this specific case, we can replace this pi of r of x square with a of x. Now what we can do is we can send this a of x to the denominator, and we'll get the remaining term rho g by 3 L minus x as sigma x. So we'll do that in the next slide. So we have again the relation for strain, relation for stress. So stress value will be n of x by x, which is rho g L minus x by 3. So we can calculate d delta in terms of strain. So d delta is epsilon of x dx, and we use a Hooke's law and replace strain with stress. So sigma of x by e, and sigma of x is rho g L minus x by 3. So d delta is rho g L minus x dx by 3e. So what we can do our integration and find the total deflection. So we do the integration from the limits x is 0 to x is equal to L. So on the left hand side, we have delta of L minus delta of 0, and on the right hand side, limits from x is 0 to x is equal to L. So L dx will be L square, and x dx will be L square by 2. So L minus L square by 2 will be L square by 2. So we will get rho g L square by 6c. And again, the point is connected to the fixed support thus, at x is equal to 0. So this point will not move, and the deflection or the elongation at that point will be 0. So delta of 0 is 0. So we'll get the expression for the total elongation, delta of L. Intermediate position we can get by replacing, I think I made an error here. Yeah, it's okay. It will be rho g Lx minus x square by 2 by 3a. Okay, so this is the expression for elongation as a function of x. So I think our class, yeah, as a homework problem, you can solve this problem. So here we have both, yeah, you can solve this problem where there is only, we have a cone with a external load P or cone with self weight. Here in this problem, I didn't show the body force, but this is a problem with cone with self weight. Okay, same thing we'll do, and yeah. So only thing is in this problem we have our external load P acting here. So n of x will be sum of rho g v plus P. Okay, so it will be P plus rho g pi r square by 3 L minus x. And then you can do our analysis and find the expression for delta of x. So you can solve this as a homework problem. Okay, so I think we conclude this class. So yeah, we have discussed this bars with continuously varying loads or continuously varying dimensions. So here both the here it is a frustum of a cone, and here the diameter is shrinking from dA to dB, and we are asked to analyze this. And you usually follow the same procedure. There's not much change. Okay.